Okay, in this video, I'm going to cover two sections because I'm going to compare them, and that is 4.3 and 4.4. Now, before I start doing problems, I just want to explain what 4.3 and 4.4 are. 4.3 is the additive rule, or the additive property, or whatever you want to call it. It's predominantly when you add probabilities. And 4.4 is the multiplicative rule. And I'll just put multiplying property, or rule, whatever you want to call it. Alright, now the reason I'm comparing them is because they both have little twerks about them, or little quirks about them that you need to make known. The first one, whenever you see the word or, you know you're going to use the additive rule. The probability of this or the probability of that. When you see the word or, that usually is an indicator that you're going to use the additive rule. The multiplicative rule uses the word and. The probability of this and the probability of that. What is the probability of this and that? And the question will ask that. Another thing about the additive rule is that you have to always subtract the overlap. Okay, this is something that you need to remember. Over here, something you need to remember is determine whether you have a independent or a dependent. Dependent is without replacement, and I'll explain that in just a second. Without replacement. Now, give you a quick example of the additive law. Let's say we have a chart, and let's say, or table, and let's say this is intoxicated drivers and non-intoxicated drivers. And this is intoxicated pedestrians and non-intoxicated pedestrians. And let's say there's 2, 4, 10, and 12. Okay? Now, one of the things that I need to tell you about these tables is don't try to figure them out. That's one thing you don't want to do, because if you try to start figuring out, you're going to drive yourself crazy. So don't do that. But let's say that we want the probability of finding a intoxicated pedestrian or an intoxicated driver. Okay, we want the, and I'm going to use a highlighter here so you will see the overlap. I'll use a green highlight, a pink highlighter. Well, I was going to use 15 out of 10 times. I'd have my highlighters handy. There's my blue highlighter. Alright, the probability of an intoxicated pedestrian is right here. Hopefully you can see that blue. If you can't, I'm sorry. Okay, that's blue. And then the intoxicated driver will be pink. Hopefully you can see that. Notice that we have an overlap right here. Here's the overlap. Blue and pink right there. Now, first of all, you get a total. Well, 10 plus that's 22, 24, 28. So 28 is going to be your denominator. And then you just add up whatever you have colored and subtract the overlap. So that will be 2 plus 10 plus 4 plus 2, or 2 plus 4. And then you minus the overlap. And your probability is going to be 2 plus 10 plus 2, that's 12, or 14, 18, 16 over 28, which is equal to 8 over 20 over 14, which is equal to 4 over 7. And that's how you use the additive law. The multiplicative law, usually you don't have a table, but you might. But the without replacement and with replacement is the factor here. And what I'd like to do here is explain without and with replacement. Let's say that you have a bag of marbles. And in that bag of marbles, you have 3 blue marbles, 4 red marbles, and 2 yellow marbles. Okay? And let's say that you want to know the probability of picking a red marble. Well, the probability of picking a red marble out of this bag of marbles would be 4 out of 4, 7, 8, 9, out of 9. Well, what do you do with that marble after you picked it? Because you got to reach your hand in and pick a marble. Alright, you got a 4/9 chance of it. Do you put the marble back in, or do you put it in your pocket? Well, that's what this is right here. Usually the problem will state whether it's with or without replacement, or it will say it's independent or dependent, or it's a question about a vote and a body count or a head count. Well, a person can't be counted twice, like let's say voting in the Congress. Well, only one person can vote for each bill. You can't vote 3 or 4 times. So when it comes to a vote, or comes to a body count or a head count, you can only be counted once. And you have to read the question, and if they do not distinguish whether it's independent or dependent, or whether it's with replacement or without replacement, then you have to assess whether you think it's with or without replacement. In this case, we're going to say without replacement. So you put that marble in your pocket. Well, what's the probability of picking a red one after you put that one in your pocket? Well, now it's going to be 3 over 8. Well, what's the probability of picking one more red one? Well, that would be 2 out of 7. Because you keep putting this one in your pocket and this one in your pocket, there's only 2 red ones left in here. So this one affects the outcome of the next one, and this one affects the outcome of the next one. So when it's affected, then you have dependent, which means without replacement. Now, let's say that you had another bag of marbles. Let's say you got a bag of marbles, and it's got the same ones in there. 3 black or blue, 4 red, and 2 yellow. And let's say that you had with replacement. What's the probability of picking a red marble? Well, that's again 4 over 9. And what's the probability of picking another red marble? It'd still be 4 over 9. And a third red marble. That would be 4 over 9. See, it doesn't change. Now, what do you do with those multiplicative laws after you do it, well then you multiply them together. Now, there's one more rule that you got to remember with the multiplicative law, and it's kind of a general rule. It's not written in stone or anything. And I usually tell my students that after 3 digits, it doesn't matter. After 3 digits, it doesn't matter if it's with replacement or without replacement. Because the probability is so close that it really doesn't matter. Let me give you an example of what I'm talking about. Let's say that you want to find the probability of picking 3 red marbles without replacement in the problem we just did. Probability of picking 3 red marbles, and this is without replacement. Okay, so that means I put it in my pocket when I get through. Well, that's going to be the first one, the second one, and the third draw. You put your hand in there 3 times. First one is going to be 4 out of 9. Second one is going to be 3 out of 8. And the third one is going to be 2 out of 7. And I would multiply those 3 and get a decimal, and that would be my answer. Okay. What would be the probability of picking 3 red marbles if it was with replacement? Probability of 3 red marbles with replacement, meaning that I put it back in the bag, would be 4/9 raised to the 3rd power. 4/9 times 4/9 times 4/9, which is right over here. But instead of multiplying those, I just raise it to the 3rd power. Now, as your numbers, see, these are 1 digits. These are just single digits. You get to triple digits, it doesn't matter. After you get over 100 or 200, after you get 3 digits, and the higher you go, 4 digits, 5 digits, the difference between these two right here is very minimal to the 10, 100,000. So just a observation for you on the multiplicative law that with or without replacement is important, but after 3 digits, the higher digits, it doesn't matter. I'd like to do 2 other examples. One with the additive rule, and I'm just going to make this an additive example. Additive rule example. And I like this example because you can do several problems. Let's see, you got blood types. I can't remember all of them, but A, B, O, and AB. Can't remember all of them, but anyway. You got positive, you got negative. Well, I can't remember if that's correct or not. Yeah, I think it is. Oh well. Anyway, you got 2, 4, 5, 3, 1, 3, 2, 4. Okay? And I want to find the probability of A or positive. A or positive. Or means additive law. Okay, additive law. So I'm going to make my A the blue. You can't hardly see that. My highlighter is awful. Let me throw it away. And that be the A. And then the positive would be there. So if I wanted to find that probability, it'd be over, let's add up, 2, 6, 11, 14, 18, 20, 24. And that's going to be 2 plus 1 plus 2 plus 4 plus 5 plus 3 and minus the overlap, which would be 2. You got to always remember to subtract the overlap, and the overlap is right there. So that would be 2 plus 1 is 3, plus 6, 11, 14, minus 2 over 24, which is equal to 17 minus 2, which is equal to 15 over 24, which is equal to 5 over 8, something like that. And that would, of course, be a decimal between 0 and 1. Now let's do another example of additive law, and I think this one's important because you're going to run into some like these. A, B, O, A, B. And I'll use the same numbers. Positive, negative, 2, 1, 4, 3, 5, 2, 3, 4. And let's say we want the probability of A or O. Okay, well that's simple, Hubert. You just highlight what you need. Yep. So A, we're going to make blue again. I'm going to use green. Let's try this green. Hopefully it works better. Oh yeah, that works a whole lot better. So there's the probability of A. And the probability of O. Well, Hubert, there's no overlap. Well, if there's no overlap, if it ain't broke, don't fix it. If there's no overlap, you don't have to subtract it. So that would be all over 24. That would be 2 plus 1 plus 5 plus 2, which would be 7 plus 3, which would be 10 over 24. And of course that would equal some decimal between 0 and 1. So if you have a table, the additive law is really simple. You just got to remember to subtract the overlap. And if there's no overlap, then you don't have to subtract it. You just add them together and put it over the denominator, which is the total. This problem is a problem that gives a lot of people fits. One procedure of this is multiplicative law, or rule, or whatever you want to call it. It says one method of a procedure called acceptance sampling. A sample of items is randomly selected without replacement and the entire batch is accepted if every item in the sample is good. A company has just manufactured 757 CDs. So there's a big case. 757 CDs. Notice we have 3 digits. So I'm going to show you that in just a second. 225 by statistics are defective. 225 are not good. They picked 3 of the CDs out. They want to know the probability of all 3 being good. Well, the first thing you got to find out is how many are good in the box, in the case. Well, that would be good CDs would be equal to 757 minus 225, and that would be 2, 3, and 5. So 532 are good. So you set up your three fractions, and that would be 532 over 757. Without replacement means you put it in your pocket, like the marble. So that would be 531 over 756. And then 530 over 755. Do that math and you're going to get some number, some decimal between 0 and 1. Now, since we've got 3 digits, we'll go ahead and do that math right quick for you. Let's see, I got to get my calculator. And that's going to be 532 over 757. Ugh, can't hit the right buttons. 532 divided by 757. And that's equal to 0.70. And then 531 divided by 756, and that's equal to 0.70 again. And then 530 divided by 755, and that's equal to 0.70 again. Well, 701.9. And then let's do the first one again. 531 divided by 756, 7023, and then 532 divided by 757, and that's 0.7027, 7028. So, and this is a 4, 7024. So, we've got 0.7028 times 0.7024 times 0.7019. I get 0.3465. Well, since we have 3 digits or more, let's just do 532 over 757, meaning with replacement. Remember I told you if it's 3 digits or more, especially on the high end, I doubt you'll have to even worry about it. So let's do 732 over 757 raised to the 3rd power, because you got 3 picks. If it was 10 picks, it'd be 10th power. So 532 divided by 757, that's equal to 0.70, blah, blah, blah. Raise that to the 3rd power, and I get 0.3470. And if you're raising to the 3rd decimal, you get the same answer, 347. So you see that without replacement and with replacement doesn't matter, especially when you're talking about the high end of the 3 digits. You know, 300 or more, 200 or more, whatever you come out with, but usually, you know, after about 200 or 300, you start to see these 2 numbers really getting close together. So I hope that helps with 4.3 and 4.4.